Okay, so hello everyone, my name is Kamil Deja, and today I would like to tell you a bit about how we do similar things at the ALICE experiment with our research group from the Warsaw University of Technology. So how we are using generative models for fast cluster simulation this time in the TPC detector. The agenda for today's talk is as follows. At first, I will explain a bit what is the ALICE experiment, what are we doing there. Then I will describe the particle cluster simulation problem. There were already a lot of, you already talked a bit about this problem, so I'll do it briefly. And I briefly describe generative models because you are also familiar with them, but I will stick a bit in this topic because of the fact that I would like to introduce to how we actually improved those models somehow for our task by applying the combined loss function from the both GANs and Variational Autoencoder or the standard autoencoder, but I come to it later. I'll show you some networks architectures which we use for the problem, and finally some results and examples. Starting with the ALICE experiment, we are at ALICE we are the most concerned about the particle tracks. So what we are trying to determine is not actually what is the we of course want to know what is happening inside the collision, but to do so we at first have to understand what are the particle tracks. So in fact, when we understand what are the tracks, we can understand what are the what particles emerge during the collision. And to understand those particle tracks, to simulate them, we need to record something in the detectors. And for example, in the most important tracking detector at the ALICE, which is the time projection chamber, we record something called at first hits. So let's assume a part of the physics which happens right there. Let's assume that we can record actually up to 159 points in the detector, which define through how the particle actually was moving through the detector. And those points are, of course, in the three-dimensional space inside of the detector. So those are restricted by the size of the detector, which is more or less 5 meters in each dimension. And also there cannot be any clusters inside of this inner field gate because there is actually another detector. So what we are thinking right now, right here, we want to simulate those points right here using generative models. Why generative models? Because current simulation process, as you probably all know, and as you all heard, is really computationally expensive. Actually, in ALICE, we have a bit more problems than in the other experiments, because what I already told you, we are mostly interested in those tracks. So when all of the other experiments simulate the events, they start, of course, with this collision generator. Yes, we got a number of particles with their initial parameters. Then they move to this node of particle propagation. So they propagate those initial particles through the detector's matter and translate them to the electronic signals, which are then recorded in the experiment. So the so-called digits. And this is where the process stops for most of from other three detectors. In ALICE, we then move a bit further. We once more translate those electronic signals, those digits, into three-dimensional space, three-dimensional points, which are in the ideal case the same as we will get here, but this time we also consider the electronics limitations and so on. So actually, those three-dimensional points are what we can actually simulate out of the real detector, out of the real data which we can record in our detectors. And our idea to this task is as follows. We at first wanted to use generative model to skip all of those 4 processes and to simulate the particle clusters out of the random noise. So we can simulate actually what is the possible output for the detector. Doesn't matter what are the initial values. But then we decided that maybe this is not the best idea, and maybe we should actually consider also this first node, because this first box to take some initial parameters of the particles and then move them to create the specific noise which we can fit into our generative model to produce the meaningful clusters, just as it would happen with the standard procedure. And our data set is actually almost unlimited. We've got like petabytes of data. We won't be able to use them for another unlimited unlimited time. So we got stick with some part of the data. And generally what we want to simulate is something like this. So the event with event, so the event, so all of the particle tracks or particle clusters which can be visible after the collision. But there is a big problem. The detector, I already told you that the detector is 5 meters in each dimension, and the resolution of the TPC is up to 1 millimeter. So you can imagine that we have like 5,000 times 5,000 times 5,000 pixels, which is huge, at least for any generative models. You saw the pictures of celebrities, which were 1,000 times 1,000 pixels, and this was the top result right now. So this is definitely not possible. So what we did, we decided that we won't simulate the whole event at the same time, at once. We will try to simulate each particle independently and then merge them together to combine them to the event like this. Thanks to this, and knowing the fact that we can record up to 159 up to 159 particle clusters, so up to 159 points, we could actually change and don't generate the image like this, the three-dimensional image, but something like this. So the two-dimensional table where we've got when we have 159 rows with positions of the clusters. And here is the first problem which we can encounter. So I said that we can have up to 159 clusters. If we have less than them, we applied some zero padding at the beginning. This can cause some problems with generation, but I'll explain how we deal with it a bit later. Particle clusters are not only the positions, also some energy associated with the particle. But we decided to implement it as a separate flow, so I won't talk about it because it's less interesting for now. Okay, so moving finally to the generative models. You're already familiar with Variational Autoencoder. I would like to only focus on the fact that once more we are, in our case, we've got this original sample, we've got generated sample, and apart from this normalization, which forces the output of the hidden layer to have some normal distribution, we are also measuring the mean square error between those, for example, mean square error between those two examples. And having those this implementation like this give us the hint that we've got actually some real example from the data, and we've got our generated example, and we've got some measure to say that okay, this is okay according to the real data, and this is not. We don't have something like this with the generative adversarial networks. You know already how do they work, but concerning the process of you training the generator, we are in 100%. We base our decision only on the quality of the discriminator. We have to. We can never exceed with our generator the quality of discriminator, because the only way in which the generator will learn how to improve itself is by discriminator which show the mistakes which it makes. And the same thing happens for the conditional generative adversarial networks, which we actually use. The only difference is in the fact that we've got initial parameters here and initial parameters here. So we use some initial parameters to change a bit the random noise at the beginning, and we use the same initial parameters to fit the discriminator. And once more, the only process which can lead to improvement in generator is to discriminator showing that, hey, under those conditions, those initial parameters, I think that maybe those three values are not okay. So maybe you should change some weights of your layers. And this is the only way we can achieve it. So there is a question concerning the fact what we are actually trying to generate, which is the physical, which are the particle clusters, which is something physically correct, which has to follow some physical rules. Why can't we actually do something like this? So can we actually use those initial parameters to somehow measure whether this generated sample is okay in terms of those initial parameters? So the question is, can we infer what output should we obtain for the given initial parameters? And the answer is, of course, why not? Once more, we have exactly the same process with the conditional generative network, but actually, because of the fact that we are right now using conditional generative adversarial network, why don't we use the initial parameters which we have already in the data? So let's imagine the scenario like this. We are taking one example from the original dataset. We are taking the initial parameters of this example, and we try to learn to train our GAN on those initial parameters. So we are once more creating some random noise. We are feeding the generator with it. We are passing those initial parameters to the discriminator, and the discriminator says the same thing. Okay, I don't like those two numbers, for example. But from the other hand, we can take the original example from the dataset. We can check that, okay, it had some values like this in those two pixels or those two tuples. But in our generated model, it has some different values. So maybe according to some physical law, it's not possible to have something like this. So maybe we should use the mean squared error star, I called it, between the real example and the generated example to actually speed up the training of the generator in generative adversarial networks. And that's what we implemented. We used more or less this mean squared error between the real examples and the generated samples to implement the combined loss for conditional GAN. So we used the standard GAN loss. We used the mean squared error between the real examples and the generated ones, and we combine those two to speed up the training. The problem you can probably probably figured out already is that we will end up with the fast model collapse, and that we may end up with generating all this time the same example as we had in the original dataset. But the answer for this problem is that we applied some parameters to the loss function, which says how much which loss can actually how the final loss should depend on each part of the loss. And if we use this mean squared error only at the beginning of the training, we can actually show the way to for the generator how it should start to produce something meaningful, leaving the discriminator loss at the end, so it won't produce all the same result, only the same results, and those are in the true data set. So moving right now to the architectures, we started with the standard multi-layered perceptron for both variational autoencoder and GANs, but it didn't actually perform well. So we pretty fast changed into some some at first recurrent neural networks, because as you can imagine, those particle clusters are pretty recurrent, but it didn't also perform as well. So we changed our thinking and decided that those are actually kind of the images what we are trying to simulate. So why don't you use convolutional networks, and they performed much better. Of course, since we had some rather deep models at the end, we decided to use the dropout and batch normalization to ensure that the training is going well. And also we applied the progressive training. The same thing which you've seen in this NVIDIA paper about the celebrities. We also applied the same idea in our method. So at first, the idea right there was to at first generate the images of celebrities with really low quality, like let's say 8 pixels to 8 pixels. And in each progressive step, the idea was to add one more layer, which is a bit bigger than the one before. So for example, 16 times 16 pixels. Add those layers both to the generator and discriminator to enhance the quality of the image. And so we start with 8 times 8, then 60 times 60, and so on until we reach this very good quality of 1000 times 1000 pixels. So we implemented the same idea, but we didn't want to generate more and more clusters because it wouldn't make any sense. We decided to implement the same number of clusters, but with the better resolution all the time. So we prepared the training set in the specific way that at first we limited the number of possible positions of the clusters to, let's say, 500. So when we actually visualize those tracks, there were visible aliasing on those, and with each progressive step, we added one more convolutional layer, and we changed the training set, allowing it to have more points, more possible points for particle clusters. So we were reducing this aliasing with each progressive step. So at first we had like 500 possible points for clusters, then 1000 possible points for clusters, and so on, until we reached the original data set with the last convolutional layers. And it performed quite well, but it didn't perform as well for the conditional approach, where the best performing method was the standard deep convolutional generative network. We used some initial parameters like particle momenta mass and energy. And we also applied this combined loss function for this model, which ended up with quite good results. What you can see right here, we are actually measuring how far we are from the standard simulation, full simulation. So we measured the distance from the ideal helix, which because the particles should fly with the measure of in the shape of ideal helix. And for the from the full simulation, you can see that the quality was around 1 millimeter, which is actually the precision of the detector. And for our method, it was still around, let's say, 8 centimeters, 10 centimeters. So an order of magnitude, or 2 orders of magnitude worse than the standard method. But what we're hoping, and what is already visible, we've got pretty good speed up comparing to this standard method. We actually measure the speed up pretty on the single CPU. We only used one core of the CPU with no GPU acceleration, and our methods were like from 25 times faster to 100 times faster, because this tracking problem is not so slow as it is for calorimeters response. But we also measured that we can have additional order of magnitude speed up when using GPUs, which is not so easy for those iterative methods which are actually present right now. Finally, some examples. On the top, you can see totally randomly chosen examples of how our method performs. So with orange, you've got the true simulation, the full simulation we've shown. With blue, you've got the simulation with our method. On the bottom, there is a whole event and the generated event. You can see that some of the tracks right here are not yet a bit strange, to be honest, comparing to the real ones. So we'll have to work a bit more with this problem, but we have some ideas. But also some histograms about the coverage of the detector. So there was this problem which everybody described, that GANs do not, they may have some problems with recreating the real data set distribution. So we measured it. We measured what is the distribution of points in each XYZ dimension of our clusters. We measured it on the whole test set of our data, and the orange one is the true distribution and the black one is the distribution of our method. So as you can see, it's not so bad actually. So to summarize, I showed you here that how we are trying to apply the generative methods for fast simulation. We don't have actually yet the same precision as the full simulation, but we have already a massive speed up comparing to the standard methods, and we can even get bigger speed up when using GPUs. We also maybe as a future work we think about applying those methods as a semi-real-time anomaly detection tool, which we were discussing a bit before. But for that we need to have some better results. We have already some ideas on how to improve the results. We've already noticed some problems. For example, the problems that we have worse results for particles with lower momenta, so the particles which have actually bigger curvatures. So we have to improve this. But we have some ideas like adding additional initial parameters or combining some architectures. Okay, so this is all. Thank you very much.
Thank you.
And I'm waiting for some questions.
Questions?
Yeah, you were a bit worried about mode collapse with your combined loss thing.
Yeah.
And then you showed some plots just of the distribution to sort of say that you don't have mode collapse, which is, I guess, true in some sense. You don't have collapse to certain values, but how do you use from that kind of plot? You wouldn't know that it didn't give you back the same training set, right?
Oh no, it's not. I haven't got it here, but we've actually measured that the generated particles differ in time. They are not the same as they are not the same always for the same initial parameters.
They're not the same as the training set.
No.
Yeah, but how do you know? I mean, how do you know that it's not a simple like shift of the training set, for example? So, I mean, how do you measure that, like the L2 distance between
what we did, we measured for the same initial parameters whether what we generated is always the same. Maybe it may be actually something.
Could be some trivial manipulation of
it could be some trivial manipulation. Maybe.
So I mean, I'm interested in this for myself, how to verify that.
But to be honest, when I'm thinking about it, we know that the shape of the particle clusters, so the shape of the track, should be exactly like this in the ideal case. So we know it should be this and not the other one helix. So the only difference we can have is is where we actually put the clusters on this helix. So there can be only some kind of trivial, in some case, some trivial changes comparing it to the original data set.
Right. But if it was trivial, then you could just do some smearing and you don't need to bother with the GAN, right?
Yeah, this is kind of true, but physicists don't like it.
They don't like this either.
So the mixing of the adversarial and somehow the autoencoder is interesting. So but because the adversarial could unstabilize your training, did you try to take it out and just do autoencoder by just?
Yeah, we tried at first with the normal variational autoencoder. We didn't try with the autoencoder without the variational part. But the variational autoencoder, unfortunately, didn't get us very good results. As you heard that the results for us were as well blurry, and they didn't really look like tracks. Yeah, so idea of this combining was only to speed up the process
But somehow you put yourself you're in a specific case where from the condition you can actually pick.
Yeah, that's true.
And then do a one-to-one, which is a specific.
This is a specific task for what we are actually doing. If we want to generate the pictures of the cat, we cannot do something like this. Yes, obviously. We can measure that. We cannot measure that the cat should follow some physical parameters, which we can do for clusters. Yeah.
Other questions? Just quickly, maybe. Do you want to get to the same performance that you get from GAN, or would you settle for something?
I don't know. If we get to the performance of Jean, it would be extraordinary with the speed up like 100 times. But because the idea of this work was to use it as this anomaly detection tool. So actually to use the generator to simulate in a fast manner the particle clusters, to compare it with the output of the generator of the detector, to determine whether the detector is actually working good or not. So we've got to try to understand with some physicists what are actually the anomalies in the detector, because it's not so easy. And can we measure it already with the generator which behaves like this or not?
Or how far you have to go?
Yeah, or how far to go.
Thanks. Are there other questions? No? Okay.
Okay, thank you.